Okay, good afternoon. So last class we introduced substitution reactions. Remember, substitution reactions are our first real transformation. This is where we're starting to use changes in either what the substrate is, parts of the mechanism, something to actually give us a targeted synthesis. So generally, a substitution reaction involves two different things. What do we call the two reagents, the two starting materials? They have special names. All substitution reactions need, one with an N. It's a nucleophile and then an electrophile. Electrophiles are special. They contain what? Electrophiles have leaving groups, right? They have a reactive center. These are the parts of the molecule where we're actually going to be affecting this transformation. This is where we're doing that substitution. Nucleophiles are special for what other reason? What are we looking for in a molecule that is a nucleophile? Charge. Charge, but what kind of charge? Negative charge. You're looking for a buildup or an excess of electrons, lone pairs in charge. Leaving groups are special. What makes a leaving group special? Give me an example of a leaving group. Yeah.
It would be a stable anion.
Stable anions like halogens, chlorine, bromine, iodine. Those are the things you're looking for typically. So we left off last time discussing the first of our substitution reactions. SN1 and SN2. Do you guys remember? We put a sound to this, and SN2 reaction sounds like it happens in one step, a single transformation. It is what kind of reaction because of that? One transition state, it's an elementary step. So it passes through this transition state. Now the unique thing, what sets an SN2 reaction apart from anything else is this concept we call inversion. If the nucleophilic attack, if the electrophile, the reactive center of the electrophile, is an asymmetric center, it will undergo inversion. Now again, this attack, this transition state, it is always happening. We're not saying SN2 reactions only undergo inversion when there's an asymmetric center. The only reason we can see it, that there's a case, if this is an asymmetric center, we have different priorities on the four different groups attached to that center. That gives us a signature, that gives us a mark to see that this transition has happened. If number 4, 3, and 2 were all hydrogens, it's happening, but it's invisible. There's no real mark to see this. It's only when there's an absolute configuration, R and S, that allows us to see that it's happening. So in this transition state, the nucleophile is approaching. Remember, it's donating its electrons into the antibonding orbital here between this carbon and leaving group. That leads to this sort of umbrellaing type motion. The carbon in the middle actually physically turns into what looks like this pentavalent system. It's not actually 5 things bonded. This is a transition state, but it flattens out. And it flattens out in a very predictable way. It literally flips itself inside out like an umbrella. As a result of that, if the priority of the incoming group and the leaving group, this would be my leaving group here, if those have the same priority, the priority number 1, which often happens, right? Leaving group is going to be something like a chlorine, a bromine, an iodine. The nucleophile coming in is going to be something negative, like negative nitrogen, negative oxygen. So what will happen is, we now have a new center. If you go and assign this, based on how this is, we're not changing these groups. 1 goes out, 1' comes in. The R center turns into an S center. We've actually changed the configuration by actually inverting that center. So we're going to practice this out. How this happens, what happens here is if we given a reaction that is proceeding by SN2, first of all, the mechanism, remember, mechanism for these reactions, we start at the nucleophile. We're going to approach, form a new bond between the nucleophile and the reactive center. I've chosen this one here. That's the carbon that contains my leaving group. That's where the reaction center is happening. If you take a look, the carbon that contains my leaving group, can I give it an RS notation? Chlorine, methyl, cyclohexyl. Yeah, that's an asymmetric center. So if this 2 electrons in, 2 electrons out, that completes the mechanism for this reaction. Now what this is going to look like when we're done, I'm going to start off by drawing everything that didn't change. I didn't touch the cyclohexyl. I didn't touch the methyl. That's the carbon fragment that was part of my reaction. The chlorine has left. I'm going to have a Cl minus as part of this reaction. I also, remember, the sodium, that's my spectator ion, it's coming along for the ride too. I could draw this as NaCl, but that's the charge balance that we're having here. Those are the pieces that are not part of the real new bond we form. We're creating a new bond by this arrow that we've drawn right here. That arrow is describing a new bond between carbon and sulfur. So the important part, as this chlorine leaves, to draw this, if the chlorine is leaving, and imagine the chlorine right now is sticking up out of the page, it means the sulfur had to approach from the back, inside the page. If the sulfur approaches from inside the page, it's going to have a geometry as a dash. It's going to be sulfur, and then the rest of the molecule. There's 2 carbons attached. That's my nucleophile piece. So the geometry used to be chlorine was up, nucleophile's coming in from the other side. It's going to displace the center. Chlorine leaves, leaving the sulfur in that position, attached to the same carbon, now with the opposite configuration. The chlorine was up, sulfur's going to be down. If you wanted to check this, we did this point here. Is this R or S up here? R, chlorine is 1, that's going to be 2, the back is 4, my hydrogen. This is going to be my number 3. That's an R center. When we're done, number 1 is still going to be my sulfur, highest priority. 2 is still the cyclohexyl. 3 is still going to be my methyl. The hydrogen is now pointing up. This is that inversion. While the hydrogen used to be down, sulfur comes in, it's going to flip that center inside out. Hydrogen is pointing forward now. So now the lowest priority group is facing us. This looks like it's 1, 2, 3. It looks like it's R. Lowest is facing you. This is now an S center. That's one way to tell that you've drawn things correctly, is to look at this configuration, right? Now, really important thing. This only applies, remember, R&S notation is only based on what we talk about here in the periodic table, the molecular weight or the atomic number. This works. This R becomes S when the leaving group was priority 1, as is the nucleophile. As long as priority 1 and priority 1 are still that major group, this is fine. There may be cases where that's not true. This inversion is always happening, though, geometrically. So that's the first part. So this one, this is also an SN2 reaction. Take a second, try to draw it out. What would the product be? Where is it happening? So you go through these steps. Identify who's your nucleophile, who's your electrophile. Draw your mechanism, what arrows connect to what, which bonds you're forming, which you're breaking. From that, now you've picked out where the reaction is happening, what we call the regiochemistry, what's leaving, and then finally you can fix your geometry. Where does the new center go? So once again, that's my nucleophile. Here's my electrophile, my leaving group. 2 arrows come in, 2 arrows out. That's the formation and breaking of that bond. Yes?
Would it be considered incorrect if we drew the arrow not like 180 degrees to the chlorine? Like if we drew in a different direction? Or does it have to be?
Like what, I guess?
Like how you have it coming from below the chlorine, basically? Like if you drew the arrow from the oxygen.
From the oxygen to the chlorine?
Yeah, well, no, not, but like to the carbon still, but just not coming from.
Oh, I see what you mean. Okay, here, let me see if I get you. You mean, you want to draw it this way?
Yeah, like is that still correct?
Okay, not too bad. Remember, the thing you have to be able to be really clear about, electrons are coming in from the nucleophile, so the arrow must start here. You're saying they're forming a new bond to this carbon. So you're trying to indicate that a bond is now existing between there. If you come in from the hook to the top or the bottom, that is not super material. I like doing it from the perspective as I did before, because it helps to remind me about the 180-degree attack, right? This is the approach that the molecule is actually undergoing. One second. This is the approach the molecule is actually undergoing here reminds me that you're coming in to displace that chlorine, so you're lining them up like pool balls. That's just my preference, but you're right. As long as there's a clear indication of where you start and stop, that's the most important. Likewise, too, the bonding electrons here are being given back to chlorine. You want to show that that bond is breaking, so here and here are the most important sort of indications, right? So that's my mechanism. Now notice, that is also happening. This is an asymmetric center. I can give it what? RS, chlorine, and the rest of it. It's 1, 2, 3, 4 is back. That's an S center. I'm predicting that I'm going to get an R geometry when I'm done. Is this an asymmetric center? Methyl. They're all carbons. If I keep going, yeah, that is an asymmetric center, right? Number 1 is probably going to be this guy because it's got, eventually it'll beat the tie. This will be number 2. This is number 3. To the back, hydrogen, that's number 4. It is an asymmetric center. Do I have any arrows touching that center, though? So should it change? No, it's coming along for the ride. So the final molecule, I'm not going to change this methyl. Nothing is happening over there. That's just part of the molecule. Yes, it's an asymmetric center, but it's not a key thing. We are changing the geometry over here. It's going to be an OH. Chlorine used to be up. OH is going to be down. My point is, it is not correct to say that SN2 reactions change all asymmetric centers. It only impacts where the reaction is happening. Molecules with asymmetric centers, that's great. We're not touching that methyl, that second center that we've assigned over here. We're only attacking the chlorine center. That's the geometry that'll change. Okay? Last one. So yeah, this is just that indication. The S center at that methyl is unchanged because there's no chemistry happening at that center. The R center, the new one here, that's where our oxygen has approached. Now, the geometry gets really easy to draw this as long as the leaving group is either in the wedge or in the dash position. What you're showing is that, okay, leaving group is a wedge, my nucleophile will be a dash, or vice versa. It's a little bit more tricky when it's in the plane of the page. If the chlorine happened to adopt one of these positions, there's still an inversion. It's a little bit more tricky to draw, so pay attention to that when you do your practice. Last one, SN2 reaction. Once again, there's a couple of features I want to point out here. We have a nucleophile, we have an electrophile. We're no longer showing discrete charges. This is, like I said, is often when we actually write these out, you write out the real salt. Sodium cyanide is what you'd actually go and use. Everybody agree this is your nucleophile? Why is that? Like, this is our electrophile because leaving group, right? That sodium cyanide is my nucleophile. If that's my nucleophile, where's my charge? Right. Sodium. Anytime you see sodium, potassium, lithium, this here, if you see this drawn, remember this is an ionic complex, which means mentally it is sodium plus the spectator ion and some anion. Be always on the watch for these components. So the sodium is what's capping this. The CN, that's your true nucleophile. The mechanism I would draw for this one is going to involve not the sodium, but the cyanide. So Cn minus will be my nucleophile to the center. Iodide is being ejected. Is this happening at the reactive site? Is it an asymmetric center? The carbon that we're actually attaching? No. It's next door to it. This center here, that's asymmetric, right? This is not an asymmetric center. There's a CH2 there. It's adjacent to it, which means that dash is unchanged. The final product you get here, we redraw our carbon skeleton. There's still going to be a dash. The reactive site is up here at the top. It's this center where that reaction actually happened, which is separated from my asymmetric center. So go slow. Identify that point. Look at the carbon that's actually attaching to it, and what you're looking for is, if the center where this nucleophile is approaching, if that's an asymmetric center, there will be an inversion. Now, we're not saying, again, the inversion's happening. It's just with hydrogens, it's silent. It's invisible. There's no way to tell that has happened, or there's any record of it happening. And more importantly, the nucleophilic attack is not involving this second center. Nothing's happening over there, so nothing should change. It's just coming through. So this one. What's the product here? So everybody all together. The electrophile is what? The thing on the left, right? Yeah. Nucleophile is hydroxide, right? That point. Where is my reactive site? Carbon that is attached to the chlorine, right? It is not going to affect this lower part of the molecule that's coming along for the ride. This is going to be my reactive site. Okay. First step, find all your bits and pieces. I've identified my nucleophile right here. I've identified my electrophile. I've identified my leaving group. I've identified my reactive site. Yes? Sorry, so to draw the mechanism with this involved? Do we have to redraw so that we show it? It is a really good idea, yes. If I just have CN, and okay, let me show, I think I know what you mean. You mean I've got iodide and I've got sodium cyanide, right? If you just drew this, right? Where are those electrons coming from? Be specific. You may know, oh, it's coming from sodium cyanide, but what part of sodium cyanide? Is it the sodium? Sodium plus. So, to be really specific, if you're given this, break it up into the ions. Now, when you draw that, you're being really specific. It is the negatively charged part of that ionic pair. It is not ambiguous at all. You're not totally wrong to do sort of that. It's just kind of imprecise. This is a lot clearer because you're being very specific that it had to come from the negative charge. Sorry. Any other questions on this one too? Okay. So on this, find your bits and pieces, and this is the same sequence for everything else. Who's your nucleophile? Who's your electrophile? Where's your reactive site? Where's your leaving group? Once you've got that set up, now you can think about where the electron flow goes. Okay. Negative from the oxygen to the carbon. Kick out the chlorine. Let's draw our product. To draw the product, you redraw. Start by drawing the parts of the molecule that nothing happened, right? Everything else. This is just like drawing resonance structures. If you're drawing arrows, part of the molecule is not being involved in your transformation, redraw those bonds. Do that part carefully and check yourself. The number one thing people drop, and when you do this, you're starting material, you're like, oh, I'm displacing the chlorine. And the number one thing people will do is draw this. Because you're so focused about, yeah, I got that chlorine, but you missed your methyl. Part of the molecule that nothing is happening must still be redrawn, right? If you just go through and you focus only on this part and you miss this part, this is not correct. You committed alchemy, it's not the right structure, you've deleted some atoms. So I always start off by drawing the molecule out. We're inverting that center. Chlorine used to be forward, oxygen's going to come in from the other side, oxygen's now going to be back, right? Yes? Bam! You blew my joke. Is that an asymmetric center? No. This is not a chiral molecule. Why is it not chiral?
That's an eternal thing. It's symmetry.
Yeah. This is not chiral. Is the product chiral? Could I give an R-S center to the carbon with the oxygen? No, left and right are the same priorities, right? They have the same RS. These guys have a plane of symmetry just based on how they're lined up through here, right? So the left and right hand of the molecule is the same. They're cutting through those atoms. There are no ARS centers. This is what I mean, though. There is always inversion. When I'm telling you about, see that there is an RS center, an asymmetric one. This is where you put up your radar. Here, though, remember, all SN2 reactions go by inversion. This is a case where, what would I call this molecule? I had another name for designations. If a methyl group and a chlorine are on the same side of a plane, it's called cis. Oxygen and methyl are on opposite sides of the ring, the plane, it's called trans. This is a way, we're still inverting it. There's a macroscopic symmetry element where the chlorine that used to be facing up, that center is umbrellaed, oxygen's still facing down, there's still SN2 happening, right? So these things, this is where, honestly, organic chemistry gets super, super complicated because we have these guidelines, but these are not, this is not court, this is not, do not approach the bench, order your honor, there's definitely been something wrong here. You said that it has to happen in asymmetric centers. No, I said SN2 reactions happen by inversion. So pay attention to these type points and follow your principles. This is still, if you follow this part through, chlorine was back, oxygen is forward, chlorine was forward, oxygen is back, everybody sees that, right? That's like, yes, that's an easy replacement. Did it happen in asymmetric center? No, but there's still macroscopic symmetry to the molecule, okay? So, that's what happens when we're talking about chirality. So SN2 reactions, what makes them special? Number one, they happen in one step. The kinetics involve two different molecules. Changing the concentration of the nucleophile or the electrophile will change the reaction's rate. That means what matters, what makes a reaction SN2 faster, the nucleophile and electrophile's nature will matter. Those can make things better or worse. Remember, what did we say? Generally, leaving groups have to be attached to what kind of carbons? sp2, sp3, sp. All of our SN2 reaction, SN1 reaction happens at sp3 centers. But what is attached to them, the electrophile itself, what its substitution will affect things. So there's these three things. Number one, size matters. If you are sitting, this is an SN2 chemistry. SN2 chemistry involves a nucleophile, electrophile have to physically approach each other. What that means is there's going to be a point in time in this transition state where they're actually really, really in each other's face. If these are just hydrogens, right? What would we call this kind of carbon here? I have a carbon here that's just on this. This is just a simple methyl group, right? There's nothing, just remember back to what we talked about for axial, 1,3-diaxial strain. Hydrogens don't take up a lot of space. The nucleophile can access sense center pretty easily. It's not too bad. If we go to a primary center, a carbon, where the reaction is happening, has a carbon neighbor. This is like an ethyl bromide now. Still okay. Not as good as methyl because we've added this extra volume. Again, this goes back to like cyclohexanes. Methyl groups do not want to have to be in the axial plane if they don't have to. They don't want to have to bump into other things. Same thing too, if we add a methyl group here, we've partially shielded that center. We've added some steric inference. The nucleophile has a little bit harder time approaching this center. If we do this, this is now a secondary center. We've added 2 carbons to this center. We've now got 2 guys blocking that center there. That gets a little bit harder. This one will be slower. So as we add steric bulk, as we go from a methyl to a primary to a secondary, the rate of the reaction is expected to get slower. It gets harder and harder to do this nucleophilic substitution because we're adding blockers. What this also means is if we go one more to tertiary, we've added 3 carbons, this totally shuts down. SN2 reactions because the nucleophile must physically get into that carbon space, cannot happen. They happen so slowly that it will find many other things to do before it does this. Yes?
What if there was like a terbutyl on it instead of like a methyl? Would that make it even harder?
So you mean, hold on. If I had this bromine, that's a primary center, right?
Yeah.
Versus bromine with a T-butyl. Still a primary center, right?
I mean, yeah.
Is that what you mean?
Yeah.
So, poll the audience. What do you think? Top or bottom? Which is probably faster? Why?
Less steric interference.
Because it's supposed to be, yeah, less steric interference. They're both primary centers. They're both in range. But you're right. If you add stuff, just like we talked about A strains, bulkiness of groups, everything we talked about cyclohexanes, it applies here. Adding bulk next to here, reaction will still happen, but we'd expect it to be slightly slower because there's a bigger shield around that center, a little bit further out. But adding bulk, just like we talked about with cyclohexanes, adding bulk to that center is the biggest way to change how this chemistry happens. Now, primary is okay. Secondary, just hanging on. Tertiary, doesn't work. Yes?
So tertiary, even if one of the groups is like methyl and it's longer, like an ethyl or just like attaching something bigger, it still doesn't happen.
Doesn't happen. Because remember, it's that local space. Methyl is bad enough. Adding ethyl is not going to make it any better or worse. You've still got this local density of carbon shielding off that part, right? So just having a tertiary center, 3 carbons attaching something with a leaving group, won't undergo SN2 anymore. So this is our first level of control. And we talked about before. SN2 reactions are awesome because we can control them with our concentrations. It's bimolecular. It means that we can choose a substrate where it will not happen. SN2 will not happen on these kinds of substrates.
So if someone was like making a drug and they wanted it to react slower, they could add like methyl groups.
Potentially.
To change the speed of the reaction.
Potentially, yep, absolutely. You can tune it up based on the type of chemistry it's happening. So, based on these, who's the fastest? Okay. On 3. Answer is 1, 2, 3.
D.
D or B we got? I agree. D is definitely the right one. So if you look through them, why can I eliminate C? Why is C out for sure? Yeah. This is a tertiary center. Not going to work. Then what we have here is a secondary. That is a secondary center. Here we have a primary and a primary. So you should be able to eliminate C. That's tertiary, never going to happen. The 2 secondaries, B and E, those are going to be slower. Now we're down to A and D. Your choice between the 2, CH2, CH2, where the group, the methyl, is further away compared to this guy over here. Yes, they're both primary, but the best one would probably be our D. It's, again, following that same logic and rules that we applied for cyclohexanes. That's how you sort of walk into this point. That's the first. What's going on with the electrophile? And what we're really saying there is, what's the environment or the steric crowding that the electrophile feels? The next one is the leaving group. In general, better leaving groups, faster reactions. And what I mean there is all based on, this is our acid base. Stable anions are going to be better leaving groups. Things that are highly stabilized, things that have resonance, something that makes that negative charge an amazingly happy negative charge, better leaving group. So this goes back to what we call conjugate bases, very stable or very, 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 very weak conjugate bases are going to be better leaving groups. So within the halogen series, this guy comes back. Iodide is going to be an amazing leaving group because it's a super stabilized species. What is this trend representing? Why is iodide so much more stable than chloride than fluoride? It's polarizable, right? Iodide is more polarizable. It's a more stable, happy anion. Fluoride, actually, on this series, is so poorly stabilized We don't even consider it a leaving group under very special conditions. So we have all the halogens. We've done two things now. Of all reactive centers for SN2, we just dropped tertiary. Tertiary will not happen for SN2. Of all the leaving groups, iodide, fluoride, bromide, fluoride, fluoride is off the list. You will not do SN2 substitutions at fluoride. They're not good enough to leave. So we've started to tighten in on what kinds of substrates are possible here. In general, you can apply your acid-base nomenclature. These 4 rules for stabilizing ions appear again here. Now there's one thing that goes against it. Everybody agree? If you had to kick these guys out, if this was going to be a leaving group, guy on the left is not as stable as guy on the right. Yeah? Because of resonance. Which means carboxylates, those are in scope. We could, if we had to, if we had a phenomenal nucleophile on a primary center, you could lose this group. You could kick out the carboxylate, just like an iodide, just like a chloride. This is a possible leaving group to have. This is not ever a leaving group. Why not? Where do we see these in terms of substitution reactions? Just bare naked O minus? What is this usually so far? Up until now, that's what? That's a nucleophile. We use that to drive the reaction to products because this oxygen minus is a starting material. That's the thing we usually want to push into the molecule. Carboxylates, these stabilized ones, they can be leaving groups. We can use that first. So where in this molecule is my reactive site? If you go through, if this is my electrophile, I've got 2 possible halogens. I've got A and B. Everybody says, why not B? This is a terrible leaving group. Even though it's a primary center, just because it's a primary center, don't let that draw your eye. Fluoride's attached to it, it's not going to be a leaving group. The only one you're going to be considering is this center here. So if we had to do a substitution reaction on this one, that's going to be our center. Just like if I was to draw a molecule that looked like this, where is my reactive site, A or B? A or B?
B.
Why? A is sp2 hybridized. You can't do substitution at these centers. This is sp2, so there's no reaction here. This one is sp3. That's valid for doing substitution. So what we're doing is we're using each of these concepts. It has to meet all these different criteria. You can't do substitution if the reactive center is, you can't do SN2 if the reaction is tertiary. You can't do substitution if the leaving group happens to be fluoride. You can't do substitution if the reactive center is sp2. So by this process of elimination, getting rid of different parts, you should be able to focus on parts of the molecule and go through. But yes, in this case, we're looking for sp3 hybridized, stable anion. Fluoride's the one that works. Chloride is the one that we are targeting. Fluoride is off the chart because it is not as stabilized. It loses that second part up at the top. So as far as that, we've got those 3 things. Electrophiles, we're looking for something that's not too bulky. Nucleophiles is the last piece. In general, what we're talking about with nucleophiles, we're looking for negatively charged species. Things that contain a lot of these, of sort of density. Now in general, surgical small is also good too, right? If we had a very, very small bullet of a nucleophile, that helps us. In general, this list is your prototypical nucleophiles. So carbon attached to an N minus, carbon attached to an O minus, to a sulfur minus, the nitrile, Cn minus. Fluoride minus shows up here again. Remember, this is not a nucleophile. Fluoride could actually be used as a nucleophile here, not as a leaving group. We can use fluoride to actually substitute things like chloride or iodide. In this series, though, remember, what you're looking for is things that look like this. They may all be masked as NH sodium, or RO potassium, or RS lithium. Each of these species may be drawn with some kind of counterion from the the metal side of the table. The sodium, lithium, calcium, something like that. But the nucleophilic portion of it is this anionic thing. SN2 reactions primarily are looking for these anionic nucleophiles. Again, this is your sort of hit list. So, of these two, which is a better nucleophile, left or right? It's kind of like asking which is a stronger base, left or right? Because, yeah, it's charged. Neutral species will lose to negatively charged species. Neutral nitrogen is way more nucleophilic negative nitrogen is way more nucleophilic than neutral nitrogen. So negative charges will dominate this sort of series. What about these two? If you had to guess, they're both neutral. Nitrogen versus oxygen. Who's a better base? Better base. Right? Like, remember, if I was to protonate these, there's going to be N plus versus O plus. Better base, your nitrogen's going to win. Under these conditions, if I had to pick those two, the better base, more stabilized sort of species, that would win across these ones. So this is fitting into this, back to our acid-base discussion. Now again, SN2 reactions, primarily what you're targeting, what you're looking for are negatively charged species. If I was going to do an SN2, these would not be my choice of nucleophiles. I would choose a condition such that I had a negatively charged nitrogen if that's really what I wanted to use. But if we have two atoms from the same row, the basicity argument that we'd use, saying which one is a better base, is also a way of identifying the nucleophile. Now there's one thing that messes this up. Back to polarizability. Who's more polarizable? S minus, O minus? S minus. Who do you think the better nucleophile is? If it was base only, you go with O minus. Sulfur does something really weird here. Sulfur's the one that wins. This goes back, and how to remember this one? This goes back to space. How big is sulfur as an orbital relative to oxygen? Bigger. Remember, what matters most? Back to methyl versus primary versus secondary versus tertiary. Size matters. What's happening here is sulfur is this giant polarizable group. And it has to form a bond to that center. Let's say this is a primary center. If I'm an oxygen, I've got to physically tuck in that electrons and run that ball in to get right into that center. Sulfur's got the ability to have a long reach. So it can stand further away. The polarizability here actually is what's helping it in this sort of case. The reason I point these things out is, again, acid-base components, why things behave as they do, these are guidelines. The practicality here is we have to balance different sort of changes to it. It works out that in this case, sulfur versus oxygen, sulfur will win. And this is why we use sulfur minus as a great nucleophile for SN2 reactions. It's got this high polarizability, and we can use that to actually sort of defeat the space requirements we have. So that's our whole point. All SN2 fits into these four categories. Number one, SN2 are second-order reactions. They have nucleophile-electrophile concentrations. Two, they go via inversion. Find the center we're doing the attack on. It's going to pop that center inside and out. Wherever the leaving group is, nucleophile will approach 180 degrees from it. The size of the groups matter. Methyl wins, primary's next, tertiary will lose. You cannot do SN2 reactions on tertiary centers. We're looking for good nucleophiles, which means negatively charged species, negative nitrogen, negative sulfur, negative oxygen. And good leaving groups, iodide, chloride, bromide. Fluoride does not count. You could do things like sulfate, right? Good leaving groups can include things like, because this, if that was negatively charged, Anything you would normally see or associate with an anion, a conjugate base from a very, very strong acid, HCl, chloride minus. H2SO4, sulfate minus. Phosphate, phosphoric acid, HPO4, PO4 minus, right? These negatively charged species are what we associate with good leaving groups because they're highly stabilized anions. That's SN2. SN1. SN1 is slightly different. It is still a substitution reaction. You still have a nucleophile, an electrophile, a reactive site. The good news is everything we do about definitions holds. There's no change. What changes is how this overall reaction occurs. Before we said SN2 sounded like, one more time, SN2 sounds like, SN1 happens in 2 steps. So with your legs, SN1 is, SN2 is, SN1 is, SN2, and you keep doing this, we. An SN2 reaction is a multi-step process with intermediates, which means it is not an elementary step. That's why it's called SN1. It is unimolecular in the rate-limiting step. SN2 is bimolecular rate-limiting step. One step where 2 molecules have to come together. SN1 starts off by taking my leaving group, and I lose the leaving group. So where SN2 started by nucleophiles 1 leaving the charge, kicking out the leaving group, now SN1 says, I don't need that chlorine, I'm done with it, I'm a strong independent carbocation, I'm fine on my own. You start by breaking this bond. So when SN1 starts by 2 electrons going to my chloride to make an intermediate. It is a carbon plus. It is a high energy intermediate. But in doing that, you fracture this, you eject the leaving group first. That's step 1. That's the first of the 2 steps. Then, now you've got a carbocation floating around. It needs to find a nucleophile. The reaction is usually done. SN1 reactions, what makes them absolutely different than SN2. SN2, we want awesome nucleophiles, negatively charged. SN1, you've made this super, super, super reactive positive charged carbon. Neutral nucleophiles are the key. Methanol, the solvent that you're doing the reaction in, will suddenly just float by and pick up our species. The lone pair from a neutral nucleophile, like methanol, will now satisfy that charge. We form a new bond to that center. Now we're not done yet. That's the done part for substitution. Leaving group goes out first, nucleophile comes in second. That's SN1. But look at your charge. When we're done this, if I took a positively charged species, the chloride's around, ionically, it's not really part of the game anymore, but it's nearby. You take this methanol, methanol is neutral. If the neutral thing adds to a positively charged thing, the oxygen's going to have to take that charge. The electrons that used to be part of this oxygen are now part of the bond. So it ends up with a positively charged species. While these are my 2 steps for SN1, to get to my final product, there must be what we call an acid-base step. We need to get rid of this proton. Leaving it on the molecule is not sufficient. We've got this positively charged final piece, that's our final intermediate. We have to lose that. How this happens is the substitution reaction is happening in a solvent. There's a ton of methanol floating around. The methanol is the one that will become your final proton acceptor. Lone pair from that methanol will end up picking off this proton to give me my final product. So this is my product. It is a long week. The proton ends up attached to here. This is double duty. This is both our nucleophile and almost always our solvent. So these are the key features for SN1. Number 1, we're going to lose the leaving group first. We make a carbocation. Second, the nucleophile is going to show up. The nucleophile is nearly always neutral. It's nearly always the solvent you're doing the reaction in. After that attack happens, you end up with this positively charged species. There's a final acid-base step that's necessary. When that happens, the solvent, another molecule of the solvent, will float by, help to pick up that proton to give us our final neutral product here. So what this means is, this is the nucleophilic substitution, leaving group loss, then nucleophilic capture. We get to this guy, we get our final acid-base step. As you might guess, making that carbocation is the hard part, which means that's our rate determining step. The first step of a multi-step transformation is the slowest. If the first step is the slowest, the overall rate of the reaction only depends on this first step. So whereas SN2 was nucleophile and electrophile, SN1 only cares about the electrophile. It's only this species because it's only that first step here. The concentration of the methanol, the nucleophile, does not matter. It won't change this reaction at all. So we're going to finish off by drawing out this. Now what would happen if I was to quadruple the concentration of my propane 1-thiol? What happens to the rate of this reaction? So this is back up. Who's your electrophile based on our two starting materials? Thing with the sulfur, thing with the chlorine? Thing with the chlorine. Sulfur, the SH, those have my electrons. That's my nucleophile. That's my propane thiol. If I change the concentration of my nucleophile, the rate of the reaction doesn't care. This is my electrophile. This is my nucleophile. That is my nucleophilic component. If this is an SN1 reaction, it's proceeding through here. The concentration of my nucleophile will not change the rate of this reaction. Doing anything that won't have any effect. Nothing's going to happen to this rate. So, if you had to look at the overall energy graph, yeah?
Just from looking at the reactions, how would you identify the SN1 or SN2?
Not yet. That's a Friday thing. But yes, but from what we already talked about, what would you guess? What did we say about the nature of the electrophile? Is this a primary, secondary, or tertiary?
There has to be a neutral.
There's two things. But the starting material is a tertiary group. Can I do SN2 on a tertiary? That's bad. Is this negatively charged?
No, it's neutral.
Neutral. Those are the two biggest hallmarks. Is look at your starting material. If it can't do SN2, it's not secondary, it's not primary. We're talking SN1. My nucleophile, neutrally charged, not SN2. We can select between these different pieces, the choice of the reactions. The other big one too, and you'll see this all the time, because SN1 reactions involve making high energy intermediates, that is your biggest head fake. That is the biggest, if you're playing poker with somebody and they've got that tell that's like, they get that deck and they're like, whoa, yeah, it might be good. If you're using heat, that's the biggest tell that you must be doing an SN1 reaction. Because SN1 reactions require us to populate this kind of an energy surface. We have to get over a monumental transition state, the rate determining step, the first one, in order to get to my carbocation intermediate. After the carbocation intermediate, we pick up our nucleophile. This last step here, so this here are the two steps of what we would call substitution. This here is my acid-base step. That's that last step where we have a protonated product that we have to lose that proton into the other system. So this is what the graph of an SN1 reaction is. SN1 reactions are multi-step. That's why we have these different components. That's why it's an overall reaction. That's why the mechanism changes. And we change it based on what we're doing. So, last thing. We talked last time about SN2 had an inversion. SN1 is a little weird. Remember the carbocation? This is the geometry of my carbocation. If this was a tertiary carbocation, it's a carbon with three things attaching to it, and no lone pairs. It's a carbon plus. That's actually sp2 hybridized. So here what I'm representing is this molecule. This carbon has an sp2 hybridization. What's the geometry of an sp2 hybridized center? It's trigonal planar. It is flat. When the carbon loses its leaving group, it chooses to have a nice life as a carbon plus, but by doing that, it changes its hybridization. It goes from a tetrahedron, loses the leaving group, and it becomes an sp2 carbon. It is now flat. Now that it's flat, the nucleophile can approach from either side of this plate. If I have a flat carbocation, the nucleophile can come from the top or the bottom. There's nothing to select it anymore. So this has massive consequences if this is an asymmetric center for stereochemistry. That's where we're going to kick off last time, guys. We'll talk through this last part, the mechanism, and then how to discuss which is which. I'll see you guys on Friday. It's easier than you think.